maybe I'll do that. Ah,
It has,
there
okay.
we go. All right.
Thank you, thank you.
No problem at all. So again, soils and urbanization is the topic today. And of course, if you want to grow healthy trees, you've got to have good, healthy soil. So good soil and good trees go hand in hand, or I should say root in soil. So conceptually, what soil actually is a lot different than what people think it is. So when we think of soil, we usually think of it as being a solid, which, you know, is certainly true. There's plenty of solid material in soil, but really soil is a combination of solids, water, and gas. And if we were to look at a healthy topsoil, this is basically its composition. It's only about 50% by volume solid material. The rest is a pretty much equal mixture of gas and water. So about 25% by volume gas and about 25% by volume water. Now I say this is a healthy topsoil, and certainly we have a lot of soil around us that is not so healthy. But if you do have a nice healthy topsoil in your backyard and your front yard, it should look something a little bit like this. This will change from day to day. After we have a heavy rainstorm, that soil is going to be pretty much 50% solid, 50% water. If we're in the middle of July and we've had a couple of weeks of 90-degree weather with very little rain, that soil is going to be much more like 50% solids, 35 to 40% gas, and maybe about 5 or 10% water. But as a yearly average, this is what we'll see in our healthy soil: 50% solid, 25% gas, 25% water. We can break it down even a little bit more than that. So about 5% of the soil by volume is organic matter, and about 45% is mineral matter. That's what the 50% solids is generally made up of. So even though there's fewer solids than we might originally think, solids are very important, and especially for us when people are describing soil and the difference in soils from one spot to another. We're usually talking about the soil solids. You know, this is a clayey soil. This is a really silty or really sandy soil. This is a nice loam. Those are soil solids. That's what we're talking about. So our concept of soil still does revolve around the soil solids very solidly, even though, again, only about 50% of the soil is solid material. So again, the mineral fraction is about 45% by volume, and the organic fraction is about 5% of the volume of the soil. What is the mineral fraction? Well, quite simply, it's just sand, silt, and clay. Those are the three fractions of solids that make up the mineral fraction. And the difference between sand, silt, and clay is their particle size. The organic fraction consists of living organisms. So the stuff that lives in the soil, we consider to be part of the soil. And then dead and decaying organisms, dead leaves, branches, twigs, manures, things like that. Now, it's a little strange, but again, the only thing that separates the grouping of sand from the grouping of silt from the grouping of clay, those three large sub fractions of the mineral fraction, is the particle size. And that's not to say that there's not a chemical variety in there as well too, differences in the molecules. Certainly there's a lot of different types of sand, a lot of different types of silt, and a lot of different types of clay. And by that we mean the molecular or atomic structure of the sand, silt, and clay can vary from one spot to another. But if we're just talking about sand, silt, and clay, what separates a particle that is defined as sand from one that is defined as silt or is defined as clay is its diameter, its particle size. And we usually use, when we're talking about plants or trees, the US Department of Agriculture's subdivisions. And they classify sand as any mineral material with a particle diameter of 2 to 0.05 millimeters. Silt is any mineral material with a particle diameter of 0.05 to 0.002 millimeters. And clay is anything smaller than 0.002 millimeters. So all these things are small by our standards. You know, there's not a large particle of sand. But if we were to somehow shrink ourselves down and actually look at these things from a different perspective, we'd see that sand is much, much larger than silt, and silt is much, much larger than clay. So clay is entirely microscopic. You can't not see a particle of clay. You can't see a particle of silt either with the naked eye. You need a microscope in order to see them. And for clay, you need a powerful microscope, like an electron microscope, in order to see, because these things are really, really small. 0.002 millimeters is the same as saying 2 microns, or 2 millionths of a meter. So if we took that meter stick, which is a bit longer than 3 feet, we sliced it into 1,000,000 equal parts and put 2 of those millionths together. That would be the diameter of the largest particle of clay. And they can get a lot smaller than that as well too. Silt is significantly larger, still microscopic. We wouldn't be able to see a particle of silt with the naked eye. Sand bridges the gap. The larger particles of sand we can see. If you go to the beach, certainly you can see individual particles of sand there. That's pretty coarse sand. As we're starting to get down to the 0.05 millimeter range, we are getting into the microscopic territory. I had a really good talk given by a master gardener many years ago, and their analogy was, if you've ever been to, I've got to get the name right, the Washington Commanders. If you've ever been to a Washington Commanders game, the particle of sand is analogous to the stadium itself. Particle of silt would be like your car, and a particle of clay would be like the parking ticket on your front windshield. So that gives you an idea of the various differences in these particle sizes, even though they all seem pretty small compared to us, compared to the human body. And sand, silt, and clay are important because they determine one of the very basic soil physical parameters, one of the basic physical parameters of soil, which is the soil's texture. And the texture is very simply the percentage of sand, silt, and clay within the soil. So when someone makes an offhand remark like, oh, I've got this red Virginia clay in my backyard, they're actually making a comment on the soil's texture. We do tend to have fairly clayey soils in this part of Virginia. That's just naturally what forms around here. But it's usually less clay than people think. So you add up the percentage of sand plus the percentage of silt plus the percentage of clay, and that'll come to 100%. The thing to remember here is you can add materials to your soil that can make the soil better, kind of sand off the rough edges of some of the problems that can be caused by bad texture. So let's say you have a lot of clay in a really sticky soil. You could do something like add organic matter to that to make it a little bit looser and lighter. But that doesn't actually change the texture, because the texture is the percent sand, silt, and clay. It does not include organic matter. So you add a whole bunch of organic matter to a sandy soil, you still have a sandy soil. It's just a sandy soil, sandy texture with a lot more organic matter than it had before. So just remember that organic matter does not change the soil texture, because again, texture is just a measure of the percentage of sand, silt, and clay within a soil. The general rules we see with texture is that the clayier soils will tend to feel a little denser, tend to be a little bit stickier, but also hold more water and hold more nutrients. Sandier soils are looser, easier to work, but and they infiltrate materials faster, meaning air and water from the surface can get down into the soil faster. But the sandy soils do a bad job of holding on to those materials. They just let the water and the oxygen pass through, and the water then flows down to the groundwater very quickly. So sand is very porous, but does a poor job of holding on to materials. Clay is very sticky and dense, but does a good job of holding on to water and nutrients. So that's 45% of the soil by volume is the mineral fraction, sand, silt, and clay. The organic fraction, only about 5% of the soil, but it's a very, very important 5%. So it consists of the living materials. So anything alive in the soil, whether it's a big thing like a groundhog or a fox, or are more commonly thought of soil organisms like our earthworms, some of our smaller insects, but especially our bacteria and our fungi. All this living material in the soil we consider to be part of the soil. And there is literally tons of living material in the soil. And it's strange, but the smaller you go as you move towards the bacteria and the fungi, even though these things are tiny and microscopic, they represent the vast bulk by weight of living material in the soil. For a teaspoon of healthy topsoil, if you could take all these little fungal root hairs, which are shown right here. So fungi are multicellular organisms. We don't extract individual organisms from the soil. What you can do to count the amount of fungi in soil is if you were able to extract all these little tiny root hairs, which we call hyphae, or sometimes when you bundle them all together, they're called the mycelium, which is sort of the network of root hairs or hyphae. If we were to take all these individual hyphae from one teaspoon of soil and lay these tiny little fungal root hairs end to end to end, we'd find that there's anywhere from about 40 yards to 40 miles of fungal roots per teaspoon of topsoil. So really lots and lots of stuff. For the bacteria, they are single-celled, so we can count individuals, and a teaspoon of healthy topsoil will have anywhere from about 100 million to 4 billion bacteria residing within. So tons and tons of material. You pick up a handful of healthy topsoil and you're almost certainly holding more living organisms in your hand than there are people on Earth. For those fungal numbers, 40 yards to 40 miles, generally what we tend to find is that areas in forest are dominated by fungi, whereas areas in gardens and agricultural fields are more dominated by bacteria. And then sort of natural meadows and grasslands are a little bit more balanced, but still a bit more bacterially dominated. Fungi tend to like to break down tough woody debris. And that's why they like living in forest soils, because what's dropping on the forest floor? Branches, dead trees themselves, a lot of that tough woody stuff. And they really thrive in that kind of environment. So when we're talking about the larger end, 40 miles of fungal root hairs per teaspoon, we really find that in pine forest, particularly. Pine forest in particular, even of all the other forests, are really, really fungally dominated, and they tend to have tons and tons and tons of fungi within their soils. The dead material is equally important. So what's feeding all that living material? Those fungi and bacteria and little insects and burrowing earthworms and larger insects, they're not just living in the soil because they like it. They're living in the soil because that's their habitat and that's where they find their food. Their food, for the most part, the base of the soil food web is dead, decomposing organic material. All the leaves that fall down in the fall, dead twigs, your grass blades when you mow the lawn and leave them on the surface of the soil. All that is food for all those critters that live in the soil. And the other important thing about fungi is, as it decomposes, it creates soil humus, which is a really great soil conditioner. Now, air and water is very important. Usually when we're describing soils, we don't describe the air and water as much. It's a little bit harder to describe than the soil solids. And it's different than our surface waters and our atmosphere, the air that we're breathing right now. And that's because it's a lot more heterogeneous, which means there's a lot of spatial variation. Soil has these little pockets of open space, pore spaces that can be filled by air or water depending on what the weather is like. But those pockets are somewhat segregated from each other. So maybe one little pocket of soil is entirely full of water and there's no air in there. Another pocket has a little mix of air and water. Another pocket is almost entirely dry and consists entirely of an air-filled pocket. They're somewhat separated from each other. So, if there's some microbes in one that are consuming all the oxygen and pumping out a lot of carbon dioxide, that little pocket may be anoxic, meaning oxygen free, lots of carbon dioxide, maybe some methane as well too. So when you go from inch to inch to inch throughout the soil, you're going to see a lot of differences in the specifics of the water and atmosphere. So it's not exactly the same as what we have up here on the surface. It's a lot more variable. And again, it's highly dependent on the activity of the surrounding organisms. All those bacteria and fungi, for the most part, they breathe oxygen just like we do. So if they're trapped in a little pocket and they're decomposing organic matter, there's a good chance that they might use up most or all of the oxygen within that pocket. Then they have to go into dormancy. So there's these little anoxic pockets throughout the soil that are oxygen free. And a lot of it is dependent on that the decomposition processes of those microbes. So generally, when we're looking at the air, the oxygen content of the air in the soil is going to be lower than what we have up here at the atmosphere. Now, the reason that it's really important for healthy soil to have this division of 50% solids, 25% air, and 25% water is that this really gives plants, specifically the plant roots, what they need. So you need enough solid material because you need physical support for our trees. If you think of a big 150-foot tall sycamore or tulip poplar or oak tree, when the wind blows and it's got all its leaves out, that's a lot of force pushing against that tree. And if it didn't have its roots solidly anchored into pretty strong material, it would fall over. The soil, even though it's only 50% solid, provides that solid anchor, that physical support for those big trees. But you also need enough water and air to keep the roots healthy. What do roots take out of the soil? They only take two things. They suck up water and they take in oxygen. So you're going to need a lot of those open pore spaces filled with water and gas in order to give the plant roots the oxygen and water it needs to keep that plant healthy, hydrated. Now, roots, of course, take up nutrients as well too, but they can only take up nutrients in the dissolved form. So really what they're doing is they're soaking up water from the soil, and within that water, there are dissolved nutrients. Um, so, it's kind of a misconception to think of roots as taking up, we think of it, they're taking up nutrients, but they're not taking up physical parts of soil. They're not sucking up silt or sand or clay particles or even organic matter particles. They're really just taking up the water and the oxygen, and the nutrients that they need are dissolved within that water. But you also need a lot of water and air to keep the microbes happy and active as well too. And that's again what this 25% gas and 25% water dispersion will give. Generally what the roots like, the microbes like as well too. So most microbes, not all, but most microbes are oxygen breathers. And they generally tend to like kind of a moist, damp environment, not necessarily saturated, but damp. And that's what makes them happy. If they have air coming in to provide them with oxygen and enough water to keep their environment moist and damp, they will generally be happy, be thriving and multiplying and creating a big, happy, healthy microbial population that will efficiently decompose that fresh organic matter as it's added to the soil through falling leaves, dead twigs, dead animals, manures, and things like that. As those happy microbes break down the organic matter, they release nutrients, some of which can be dissolved and then taken up by the plants as they soak up water through their roots. So how does the soil attain this nice balance of 50% solids, 25% water, 25% gas? Well, we talked about soil texture earlier. That's one of the big basic soil physical parameters, soil physical characteristics. The other one is soil structure. And soil structure refers to how the soil solids are arranged together. A soil with good structure generally tends to maintain this 50% solid, 25% water, 25% gas balance. What is soil structure? Basically, it's simply referring to how the soil solids clump together, how they aggregate. If we're looking at soil from a distance, it looks like a solid. As we get up close to it, we can see it actually is composed of these little discrete aggregates, which we call PEDs, P-E-D-S. Each one is an individual PED, a little clump of soil, basically. And between each clump, what separates one PED from its neighboring PEDs are macropores, large pores that allow air and water to get down into the soil. They're basically the channels, the highways of the soil, if you will, that allow materials from the surface to soak down into the soil and get down to the roots. So here's some good pictures of various types of soil structure. Typically what we'll find is we'll have granular structure up in our topsoil. It kind of looks like grape nuts. If you've ever had grape nut cereal, eaten grape nut cereal, it's just these small, a couple millimeter to a couple centimeter size diameter oblong PEDs. As we get deeper down into the soil, we get blocky structure, which in shape is pretty much the same as granular structure, but the size is bigger. And the reason for that is as you get down into the subsoil, you generally tend to accumulate more clay. So again, the shape doesn't really change, but the size does because more clay allows those larger blocky PEDs to form. Fortunately, what we find a lot of in urban areas is platy structure. And that is often what occurs when you take a nice, well-structured, loose, easy to work soil that has nice granular or blocky PEDs, and you compact it, you squash it under a heavy weight, which happens a lot in urban areas because we're constantly constructing things. We're laying down roadways, we're walking on the soil, we're driving vehicles across the soil. And basically, construction is sort of the big cause of urban compaction. So think of all those bulldozers and other heavy machinery that is running over the soil when a new house or a new shopping center is being built, that squishes the soil down and creates these flat, tightly interlocked platy PEDs, which are not free of macropores, but they generally have a lot fewer macropores than our loose, granular, or blocky structure. And because they have less macropores, they're less able to transmit water and air from the surface down into the soil and down to the rooting zone. But beyond what the structure is and how we can harm it through compaction, how is it created? How do these individual particles of sand, silt, clay, and organic matter start clumping together? Well, you really need two things. You need binding agents to sort of be the force that causes materials to aggregate and stick to each other. And then you need burrowing agents, which can come in and create the pore spaces between each and every ped. So what are some of those common binding agents that we see in soils? The big two are clay and organic matter. Clay sort of makes sense. Clay is sticky in and of itself. You get a lot of sticky clay there. That's a great binding agent, a great natural glue that'll cause other materials to start sort of glomming onto the edge of the clay and creating this ball. Organic matter is very good at that as well too. As organic matter decomposes, it becomes this humus material, and humus is really good at binding other materials and sort of forming the nucleus of these soil beds. Microbial decomposition is another important binding agent. As microbes, bacteria, and fungi break down organic matter, some of the byproducts they create are sort of these sticky mucus-like materials that are actually called mucilages, which again are great at binding materials together. And then there's fine root hairs from the plants as well, and from to a smaller extent, literally smaller, more microscopic extent from the soil fungi as well too. Think of the root hairs, those really small, fine roots, as being like twine that's sort of connecting and binding a whole bunch of these really small peds together into a larger one. So if we only had binding agents, though, the whole soil would just be one sticky mass after enough time. So we need something to come in and sort of break up the soil and create those pore spaces that separate one ped from the other. One of the most obvious ones is worms. Worms are sort of nature's tillers, nature's burrowers. They're constantly munching their way through the soil, making little channels. Those channels are then great pathways for water and air to follow down through the soil. Roots are fantastic burrowing agents as well. So the fine root hairs can kind of act as binding agents, but the larger roots, as they're pushing their way through the soil, their roots are constantly growing and dying back, growing and dying back. So as the root grows, it's creating a new channel. As it dies back, the root shrivels and it leaves this open pore space in its old root channel, which again is a great way for water and oxygen to flow through the soil. There's plenty of other burrowing organisms out there as well too. On the larger scale, that groundhog or the fox that I showed, obviously when it rains, there's going to be a lot of water going down that fox burrow. But other things like burrowing beetles, other insects, thousands and thousands of insects are constantly digging through the soil, creating their own channels, just like the earthworms and roots. And then there's the purely physical, non-biological forces, the wetting drying cycles, the shrinking swelling cycles, and the freeze thaw cycles. When soil wets, it usually expands just a little bit. And when it dries, it contracts just a little bit. And that kind of continuous expansion, contraction, expansion and contraction will eventually kind of crack up the soil and create these nice channels and pores. Shrinking and swelling is sort of like the wetting drying cycle on steroids. There are types of clay with certain mineralogy that when they get wet, they expand greatly. And when they dry, they shrink greatly. Now, this can be a real pain because we've got this soil around here and some people have it under their house and it actually can lift up your house and crack your foundation, which is obviously a bad thing. But out in the field in natural areas, it can be quite useful because again, the shrinking swelling can create those pore spaces over time as it shrinks and swells over many seasons. Eventually, some large natural pores can form. And the freeze thaw cycle is the same way too. And we're actually seeing this right now. If you go out and look at your garden after a heavy freeze, what you'll often see is little ice crystals coming up right out of the surface. And oftentimes they'll have little particles of clay, little particles of soil, little peds sticking on top of them. When water in soil freezes, or when water anywhere freezes, it actually expands a little bit. Ice is less dense than water. So when water freezes, it expands somewhat. And of course, when it thaws, it shrinks back down to the volume it inhabited as a liquid water. And this freezing, thawing, expansion and contraction of that freezing and thawing water will eventually create good pore spaces, especially up in the top of the soil near the surface and above the frost line. So that's soil structure, which seems like such a simple thing, such a basic thing, but it's really a really important thing. And it's one of the soil structure is one of the physical parameters of soil that suffers greatly during the urbanization process. So it's one of those things that we want to get back in order to make our urban soils healthy again. stepping back and going a little bit more basic, let's talk about soil formation. So generally at the beginning, soil starts off as solid rock somewhere. And then over time, natural weathering processes and erosion processes start breaking down that solid rock into smaller and smaller pieces until it eventually forms sand, silt, and clay. And erosion is constantly moving that material around and depositing it in new places to create soil in different spots as well too. So the combination of that natural weathering and erosion of hard bedrock is what creates our soil. But there are really five processes, five soil forming factors, if you will, natural forces that create all the soils that we see throughout the world. And they've got this great but terrible acronym. It's terrible because it's just not a very good acronym, but it's great because as being such a bad acronym, it makes it memorable. And if you remember it, then you'll remember the five soil forming factors. So the acronym is CLORPT. I think it sort of sounds like if you take a pebble and you throw it into the middle of a pond, when it hits the water, it makes that sound, CLORPT. So if you can remember CLORPT, you can remember the five soil forming factors. It's a little odd because there's 6 letters in CLORPT. There's only 5 soil forming factors, and that's because the CL, the first 2 letters, stand for climate. And climate, there's a lot of things that go into climate, but the 2 big parts of climate are temperature and precipitation. And the general rule that we find is the hotter and the more moist a climate is, the quicker things weather. The quicker things break down, the quicker that big piece of bedrock breaks down into sand, silt, and clay, the quicker organic matter breaks down into soil humus. So soils in very hot, moist environments like the Amazon rainforest is kind of the prototypical example, tend to be very deep, very weathered, and just very, we would say, very highly formed. Basically, they've been sitting there as fully complete soil for a long, long time just because things break down very quickly. Organisms, the things that live in or on the soil, are very important towards creating the final characteristics of the soil. And I gave one example, the breakdown of organic material. So obviously, if we're adding organic material, which we are, no matter where we are in the world, things are growing, things are living. And as those things will die, leaves will fall in the autumn, trees will fall down, they will shed branches during windstorms, animals will die and their carcasses will return to the soil, animals will drop manure, which returns to the soil. We will drop manure, which oftentimes is returned to the soil as well too. If that material was not broken down, we'd literally be buried in our own waste. But luckily, we've got those billions and billions and billions of fungi and bacteria in the soil. And all that dead organic matter that's being deposited on the soil, that is their buffet. They love to eat that stuff, and they're breaking it down, turn some of it into carbon dioxide, which goes back into the atmosphere. They take a significant amount and they add it to their own bodies. Of course, they're eating it because they want to grow and reproduce and create new versions of themselves, but they're also sending some of it into long-term storage as soil humus. Humus is sort of the hard to decompose end product of organic matter decomposition. And humus can actually stay in the soil for 50, 100, 150 years or so. It's really tough to break down. So organisms are important for the breakdown of organic material, but also for the addition of organic material. Obviously, why is that organic material being added to the soil? Because the leaves are dropping from the trees, because our certain organisms or certain plants will die back during the fall and winter, and their stalks will decompose and become part of the soil. So they're both the cause of organic deposition and the breakdown of organic deposition, the soil organisms. Relief. Relief is just another word for your landscape position, your topography, your slope, where you are in the landscape. And this one is kind of an obvious one, where if you're on a steep slope, generally you'll have a soil that's pretty eroded naturally. If you are down at the bottom of the steep slope near the stream valley or in any valley really, that'll be an area of deposition because material is being eroded off the steep slopes around. Where does it go? Material is very predictable. It goes to the low point. It always goes down. So it's going to go downhill, 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 and deposit down in the valleys. As a result, we go up our steep mountains. We'll see that the soil on the side of those mountains tends to be fairly thin, fairly shallow. You don't have to dig down very deep to get to bedrock. And it's usually kind of gritty and not very fine. meaning there's a lot of sand, there's a lot of gravels within it. Why? Well, every time it rains, that rainwater flows quickly off the flanks of that steep slope, and it picks up the smaller materials, the silts, the clays, some of the fine sands, washes them away, erodes them away. What's left behind? The bigger stuff that's heavier, that's harder to erode. So that soil never gets a chance to get very deep, because every time it rains, maybe a little bit of the topsoil is stripped away, especially those fine materials. But down at the bottom of the hill, next to the stream where things flatten out and you're near the floodplain, there's deposition. The material is eroding. It's depositing from the steep slopes on that flat plain. So that soil can be very, very deep. And after a heavy rain, especially if there's a flood, you might see an inch or two of new deposition just lying right on the soil surface. You can see this too if you go out to a place like Riverbend Park along the Potomac, where some of the lower walking trails are within the floodplain. If you go to Riverbend after a heavy storm, it seems like one of the park employees came and sort of resurfaced the walking trails with sand. But of course, it wasn't the park employees, it was the Potomac River itself. You get a nice inch of fluffy, newly deposited sand almost every time you have a big storm, because Potomac rises, it spreads out over those low walking trails, drops its sand load, and then eventually it retreats. Parent material. So just like we get traits from our parent material, they pass their genetics on to us. Soil gets a lot of its chemical and physical traits from its parent material, which is the rock or sediment that it weathered from. So for instance, in Fairfax County, we go out to Western Fairfax County, you'll find an area called the Triassic Basin, which is around Chantilly and Dulles. That area was an old lake, hundreds of millions of years ago. It was a very large lake, but that lake over time silted in. There also were some volcanoes around there as well too. So we find a couple of very different rock types, bedrock types out there. Most of the bedrock there is fine grain sandstones and siltstones that formed from these fine silts and sands that filled up this lake and eventually hardened into sedimentary sandstone and siltstone. But in a few spots, we see this igneous volcanic diabase rock that's come. It didn't quite come to the surface. It was basically lava that cooled just below the surface, but it's a very different rock type than than the sedimentary sandstones and siltstones. It's easy to tell where those rocks are by the soil types that you can find right at the surface. The sandstones and siltstones tend to make sort of a really dusty red, somewhat acidic, not particularly sticky type of soil. But on top of the igneous rocks, the diabase rocks, you get this really, really sticky, almost pottery clay-like soil. It has a high water table because water just can't percolate through that clay, so it just sits and soaks on the top. So you get these really sticky, soaking wet areas of soil out there next to these dry, dusty red soils. And you know by looking at them, even though they're only about 50 feet away, you can say, aha, if I dig down below that dusty red soil, I'm going to find siltstone and sandstone. If I dig down below that really sticky clay soil, I'm going to find igneous diabase rock. So that's just one example of how the different parent materials, the material from which the soil weathers, can really create very differing soil types, both in terms of the chemical traits and the physical traits of the ultimate soil, the resulting soil. And then finally, there's time, which is sort of a master variable. It's estimated that it takes about 100 to 500 years to create every inch of soil. So climate, organisms, relief, and parent material, they're acting on soil right now, they're creating soil right now, but they're creating it very, very slowly. So it's not necessarily a process we can see for the most part, because it just takes, a couple hundred years to really create visible new depths of soil that we would recognize. That's how soil is formed. Those are the natural factors or forces that form the soil and turn solid bedrock into those sand, silts, and clays. But what does soil look like if we were to start digging down through the soil? We'd find it's actually quite variable. It's going to change quite a bit from the surface of the land down 3, 4, 5, 6 feet or so. And what we find is that it's a layered system. Soil consists of natural layers, and we call each of these layers a horizon. So up at the top, we have our A horizon, and this is what we commonly call the topsoil. It's the first layer just below the surface, and it's very rich in organic matter. you can almost always tell where the A horizon is just by its color, because it's going to have this nice dark brown to black color. Why? Because it's full of organic humus. Humus is basically a black material. If you have a compost pile, what you're doing is basically creating your own humus. So that finished compost is the color of humus. You mix this humus in with the soil, it stains the soil that dark brown or black color. Now, generally in Virginia, even in a really healthy forest, you're going to be lucky to get 3, 4, 5 inches of A horizon. Just naturally around here, given the plants we have, the climate we have good A horizons. They're just not thick. You go out to the Midwest and to some of the former prairie lands like in Illinois or Iowa, you can naturally get 18 to 24 inches of A horizon. But here, I'd say 2 to 4 inches is about our average. So even though it's very thin, the A horizon is very important because it's so full of organic material and decomposing organics and humus. It's where it's sort of the biological powerhouse of the soil. Because all that organic matter is there, all the microbes, bacteria, fungi, fine root hairs, they're all there as well too, because they're after the nutrients that are sort of sloughing off that decomposing organic matter. So even though it's a fairly thin layer, it is the biological powerhouse of the soil. Below the A horizon, you can sometimes, not always, but sometimes find an E horizon. And this is, I think of the E as standing for exit. It's sort of the layer that things have leached out of, washed out of. As the A horizon forms and the organic matter decomposes within it, it creates a lot of natural acids, which gets washed down through the soil every time it rains. And the E horizon is sort of the victim of those natural acids. Basically, the acid washes through the E horizon and strips out a lot of the materials that otherwise would color that soil. Things like organic matter, they get stripped away. Things like iron oxides and other oxides of elements and metals, they get stripped out as well too. And what's left behind is sort of this leached, pale, grayish, whitish color. This is kind of an extreme example. We usually don't see E horizons quite this clearly. I'd say there's probably E horizons in less than 50% of the soils in Northern Virginia. But if you do see it, it's probably going to be a little more subtle than this. It just basically kind of looks like the A horizon. If you imagine the A horizon was a sweater that you threw into your washer on the highest possible temperature, what happens? A lot of the color bleeds out. So it just sort of looks like a bled out version of the A horizon, a little bit lighter, a little bit more pale, a little bit grayer. And again, like the A horizon, E horizons are pretty thin, usually only about 2 to 4 inches or so. What we do have, almost all of our soils around here, and we do have in very thick layers, is the B horizon. You can get 18 to 24 inches of B horizon without much of a problem in Northern Virginia. What is the B horizon? It's the clay layer. So when people are complaining about red Virginia clay, what they're really talking about is the B horizon. It's the most clayey layer, and it's generally the most colorful layer too. Our clays locally are generally coated with iron oxides. So we think of clay as being red, and that's not entirely true. It's actually the iron oxide coating on the clay that is red. The clays themselves are usually pretty gray, but when you find clays, they're almost always covered with this iron oxide coating. So it's understandable why people think of clay as being a kind of a reddish color. That's not the only color you'll find. You'll find yellows and you'll find oranges as well too. But if you're in a layer in the subsoil that is very red, yellow, or orange, feels pretty sticky and dense, most likely you're in the B horizon. And here again, we can get pretty deep depths of B horizon. 2 feet is not an unusual width for the B horizon. And they're generally, B horizons are generally a lot thicker than your A or your E. Why does it form? Well, actually, a lot of the clay is forming up at the top in the A and the top of the E horizon. But remember, clay particles are very small. So when water passes down through the soil, it picks up these clay particles over years and years and years and years, and gradually washes them down and deposits them in the B horizon. So over time, as the soil ages, that B horizon will actually get thicker as that clay is driven and deposited deeper and deeper and deeper by continuing rainstorms. Below the B horizon, below our sticky clay layer, we get the C horizon, which is sort of a border layer between the highly weathered A, E, and B horizons above it and the unweathered rock or parent material below it. So it's kind of both soil and not soil in the same way. It really is sort of like the first layer of soil that forms. The analogy I like to use is, imagine you're a sculptor and you've got this big chunk of granite in front of you and you start going to town on it with your chisels. After a couple hours of chiseling away and beginning to get the shape of your statue, you look down at your feet and you see your shoes are covered with sort of a fine mix of dust and small rock chips or gravels. That's basically kind of what the sea horizon is. It's really physically pulverized bedrock that hasn't chemically weathered yet into the very chemically different A, E, and B horizons. Basically the same chemical structure as the bedrock, it's just been ground up, broken down into much smaller pieces. It can be tough to determine where the B horizon ends and the C horizon starts, because it can be a very gradual transition from one to the other, and the colors don't always really change all that much. But usually what I look for as you're going from the B to the C is you will start to see a reduction in your clay content. So the soil generally start to feel loose, kind of more powdery and fluffier, less dense and sticky because the clay is dropping out. Sometimes you'll then begin to see more larger particles, maybe sands and gravels. So if it's sort of loose, drier, less sticky, a little bit more gritty, filled with more noticeable gravels and larger gravels, that probably means you're getting down into the sea horizon. And then lastly, we've got our B horizon, which is our solid rock. So if you're hitting solid rock, time to stop digging. You've hit the B horizon. No matter where you are in the world, you will hit eventually solid rock, but the depth you have to dig to get it varies greatly. So for instance, if we were to go across Northern Virginia, Prince William County and Western Fairfax County have a lot of that Triassic Basin, shales, siltstones, sandstones. Typically out there, not sure exactly why, but bedrock is pretty shallow. You dig down 2 or 4 feet, chances are most places there you'll hit bedrock. You go into the center of Fairfax County or Northern Arlington. A lot of metamorphic rock out there. You might have to dig down 10 to 20 feet to hit bedrock. You head into Eastern Arlington or into basically any part in the city of Alexandria, you're within an area called the coastal plain. And that soil formed from materials that were washed in from the ancient Potomac, and in some cases, the ancient Atlantic Ocean as well, too. So those soils formed from water deposited bands of sediment, not bedrock itself. There's still bedrock there, but you might have to dig down 100 to 300 feet within Old Town Alexandria in order to hit solid bedrock. You have to go through a lot of marine and river sediment bands before you hit that solid rock. So there's really a tremendous range in the depth to the rock, depending on where you are in Northern Virginia. So what does a healthy soil and plant system look like? Actually, before I get into that, this might be a good time to take a minute or two to see if there are any questions.
Well, there are no questions, but I know a lot of people are going to be interested in hearing a lot more about how development affects soil and trees. But I know that you get into that towards the end of your presentation, so I won't ask the question now.
Okay, sounds good. And yes, we will get into it in the second half here, which I will begin right now. So again, what is a healthy soil and plant?
Dan,
yes.
There was one question.
Sure.
What was the term you used for the part other than the red clay pieces?
I don't know. I have to be a little more specific. If the person who asked that question they can unmute themselves and ask directly.
Oh,
maybe.
In which horizon do you find the tree roots?
Oh, well, I would say we don't typically have really deep root systems around here. Most of our tree roots are going to be within the top foot. So that would put most of your roots within the A, E, and top of the B horizon. Although there will be some that get down in the C. There will be some that get all the way to the R horizon as well, too. But I'd say generally, most of your tree roots, 90% or so, are going to be found in the top foot. So that'll put them in the A, E, and part of the B. And most of the fine roots will be up in the A horizon. So the really, really small root hairs, because the root hairs are the active ones that are taking in water, taking in oxygen. And where are they going to find that water and oxygen and the associated dissolved nutrients that are within the water? That'll be up in the A horizon, where you've got all that organic matter decomposing. All right. Any other ones?
No,
Okay. I will continue, and hopefully there'll be a few questions towards the end. All right. So a healthy soil and plant system, what does that look like? Well, what you want to see is an A horizon with lots of organic matter and that nice granular grape nut-like structure. So it's sort of really loose. It's got these well-maintained soil pads that don't dissolve when it rains. They can hold together in the rain, but they've got these nice big macropores between them that allow that rainwater and that oxygen to soak down quickly into the soil and get to the roots and to the microbes. Within the soil, you're going to have lots of microbes in the A horizon, breaking down organic matter. And as they're breaking it down, they're releasing mineral nutrients, which dissolve in the water and then can be taken up by the plant roots. And there's that good, what we call crumb structure, granular structure. But when a granular structure is really nice and loose, you can almost just sort of dip your hand into the soil and come up with these nice visible beds. And with very little force of your hand, you can pull this stuff up because the soil is so loose. So that's what crumb structure refers to. And a structure like this is great at infiltrating both oxygen and water, allowing that oxygen and water to quickly pass down into the soil. The water dissolves those nutrients, and the dissolved nutrients are then taken up by the plant roots. So all that good nitrogen, phosphorus, potassium, iron, zinc, calcium, magnesium, that all gets to the plants and helps them power their new growth. And of course, it's a continuing cycle. It's a self-reinforcing cycle, because as those nutrients get into the plants, as the water gets into the plant roots, it helps create healthier plants, which put on more mass, put on roots and new shoots. And the more roots and shoots and fruits and flowers that they create, obviously all that stuff eventually does die, and it goes back into the soil and creates a new stock, a continuing stock of organic matter for those soil microbes to decompose and cycle their nutrients. You know, a B horizon with a lot of clay is actually pretty good. It can be somewhat of a pain if we're digging a hole, especially in the middle of July when things are really dry. That clay can feel pretty brick-like. But clay does a lot of good things for soil fertility. Clay retains a significant amount of deeper water as it percolates down through the soil during rainstorms, and that water can be taken up by some of the deeper roots of your trees. You know, it's not nearly the biological powerhouse that the A horizon is, but there's still going to be significant breakdown of organic matter and release of nutrients in the B horizon as well too. Again, not to the level of the A horizon, but still quite a bit. And then there's soluble materials. Let's say you have some nitrate fertilizer or something that you add to your soil and you have a big rain. Nitrate is very known to be very soluble. It dissolves very easily. But a lot of it's going to get, as it passes down through the soil with the rainwater, a lot of it's going to get filtered out by the clay. Clay does a very good job at filtering out dissolved materials, preventing it from getting down into the bedrock. Not the bedrock, the groundwater. Your C horizon, generally again, sandy and gritty, but that's not a bad thing. This allows for some water retention. Again, it's not going to absorb water like the clay B horizon or the organic matter rich A horizon, because both organic matter, especially humus and clay, are really attractive to water, whereas sand is not so much, but it'll hold some. And this water will be accessible by some of the deepest roots of the plants. So during a really bad drought, if a plant can get its roots down into the C horizon, there'll be some water for it to drink. And again, it does a good job of also filtering out soluble materials. It sounds strange, but if you pass dirty water through dirt, it actually comes out cleaner on the other side. So the more the C horizon that this water passes through, the more it will be cleaned before it eventually flows down into our groundwater. And of course, the water that does pass through the C horizon will get to the bedrock, find fissures and cracks in the bedrock, and get down into our long-term groundwater storage. Now, for urban areas, whenever we develop the land, it causes a lot of changes into the soil. And unfortunately, almost all of those changes are bad. One of the most recognizable changes that we see is compaction. So as you can imagine, if you take that nice, well-structured soil, it's loose, it's got that crumbly crumb texture, low density, lots of pore spaces. What happens when you run over it with a backhoe, bulldozer, pack it down, compact it to put houses on top of it, put roadways on top of it? it gets compacted. It becomes a lot more dense. A lot of the soil structure gets pulverized, the soil gets packed down, and a lot of those pore spaces get squished out. So what's left behind is a much denser, harder soil than what was in existence before. So we might originally have had 25% gas, 25% water, 50% solids. After compaction, we lose that pore space. There's not nearly as much pore space to allow that air and water to exist. So it's got to kind of squeeze itself into whatever little bit of pore space is left. And this, of course, reduces the ability of air and water to percolate, infiltrate down into the soil from the surface. If there's not as many pore spaces, or those pores are much smaller than they used to be, soil gets clogged very easily. You have a heavy rainfall, that rain is not going to percolate down entirely into the soil. Quite a bit of it could become surface runoff. And I like to call compacted soil impervious light. An impervious surface is a surface like concrete or blacktop that won't let any water pass through. Compacted soil will let some water pass through, but it can be, you can grow a nice stand of grass on compacted soil. So we don't always see the problem with compacted soil, but there's a lot of compacted soil out there, and it is acting as a sort of semi-impervious surface. So I think impervious light is a good way to describe it. So here's your well-structured soil, those nice beds separated by pretty big macropores. The water comes through and it just passes through really, really quickly. Take that same soil and we squish it down. Now we've got that platy structure. There are some pores, but they, are very horizontal. They're not as big or as open as they used to be. Their diameters have been squished, and there's just not as many of them either. So that same rainstorm comes, some water passes through, but a lot of that water gets pooled on the surface and can then become surface runoff, stormwater runoff. So you probably have seen a diagram like this, which shows the difference between rainfall falling on a very natural landscape, or at least a very impervious landscape, versus a very city-like urban landscape. When water falls on, an area of forest and farm fields, about 50% of it infiltrates, percolates down into the soil. About 10% becomes runoff. About 40% is evaporated or transpirated back up into the atmosphere. Transpiration just means taken up by plant roots and then evaporated through the leaves. In a much more urban area, that rainwater falls down, the infiltration proportion decreases significantly. Now it's only 15%. The evapotranspiration decreases somewhat. Now it's 30%. Where does the rest of the water go? It becomes surface runoff. So that's the only thing that we see really increase. Everything else decreases. The other issue with compaction is that it creates a very dense, very strong soil. Plants need to send their roots, they burrow their roots through the soil in order to grow their root system. And by growing their root system, they allow themselves to grow bigger. A plant can only grow as big as its roots will allow. And it can be, in the most compacted soil, it can be almost impossible, difficult to almost impossible for roots to even penetrate. If the soil is really, really densely compacted, the roots just don't have the strength to push through. And in that way, the roots become stunted, they're not allowed to grow, and the plant will never grow much either. So this is sort of a typical scene here. On a new subdivision, you see them plant those street trees, in the little strip of grass between the sidewalk and the street. It'd be interesting to come back in 15, 20, 30 years to see how these trees are doing, to see if they're actually growing, because it may be that they just stay at this size because the soil around them is so compacted that their roots can't grow, can't force their way out into that compacted soil, and thus they're just sort of left as almost like a maxi bonsai tree in a way. They're sort of kept in a perpetual state of poor growth. And this is a good example. This is Pennsylvania Avenue between the White House and the Capitol. Same types of trees on either side. I think there's some sort of oak. Planted probably at the same time. As you can see, these trees are in tree boxes, kind of sandwiched between the roadway and many lanes of traffic and this pretty wide sidewalk. There's soil underneath this sidewalk, and of course there's soil underneath the roadways too that these trees could access, but that soil is going to be so compacted that I don't think these trees have the ability to send their roots out into it. That soil is just too dense and strong. So what happens is the soils are basically limited to this little strip of grass underneath these planters. And what happens to them? You can see they're all kind of spindly and stunted, especially compared to the trees on the other side, which probably are not growing in great soil either, but at least they have access to this much wider strip of open soil between the sidewalk and the building over here. And as a result, the roots can grow bigger, and the trees grow proportionally bigger as well too. And you can see how much larger and healthier they are than these spindly ones that are stuck in this sort of narrow coffin, if you will, of soil between the almost impermeable urban soil below the sidewalk and roadway. And to bring back to a local example, my office actually did a contract project for Arlington County last summer, where we did a study of lawn soil in new versus old residences. So we looked at a couple houses, 5 houses that were built in the 50s, 60s. Average age was about 64 years. And then we compared it to new houses that were still under permit. Basically, they were still owned by the developer who was getting them ready to sell. And the average age of these houses was 2.4 years, although they're probably a little younger than that. That's basically the age from where their permit was first opened. And these are 2 of the actual study sites. So old house on the left, new house on the right. And what we did is we did a bunch of measurements of the soils within the lawns of each of these houses, both new and old. And we found that the average density for the new houses was 1.37 grams per centimeter cubed versus 1.15 grams per centimeter cubed for the soil in the old lawns. It doesn't sound like a big difference, but it's about a 20% increase in density for the new houses. But where we really saw a difference was the average infiltration rate. This is the rate at which water percolates from the surface down into the soil. We measure this very simply. We basically take a big ring, we pound it, big ring of sheet metal, we pound it into the soil, we fill the ring with water, and we measure how quickly that water drops. In the new houses, it was 0.13 inches per hour, so about 1/10 of an inch per hour. In the old houses, the lawns were infiltrating 1.28 inches per hour. So it was about a 90% decrease in the infiltration rate from the old soil to the new. So really, really different, even though if you look at this new house, we've got nice green grass growing on. Well, in all cases, for the new houses we saw, it was sod. Sod on top of pretty bad compacted urban soil. And that can be a real problem, not just for this homeowner, it can be a problem for the homes next to them, because let's say you have a big rainfall is falling on this newly sodded, compacted lawn. Most of that rain is going to become surface runoff, and that runoff can flow down to the neighbor's yard and potentially cause some flooding or other damage there as well too. Another thing we see in soils in urban areas is mixing, sort of mixing and pulverization and sort of homogenization of the soil horizons or layers. So the soil layers, as soil is developed, they all get mixed together. This causes the death of fungi. So remember, fungi exist as these really long, thin root hairs. When construction machinery breaks through the soil, it cuts these fungal root hairs and can kill a lot of that fungi. It also causes the fertile topsoil, again, that 2 to 4 inches of A horizon that we have up at the top, to generally be dispersed and spread throughout the depth of the soil profile, which can be very damaging too, because you really need that concentrated biological activity occurring at the surface in order to get the nutrients to those fine root hairs. When you take that area of concentrated biological activity, mix it throughout the entire soil, you basically deplete its energy to provide nutrients in a easy concentrated form to the roots. And this is sort of what you're left behind, just sort of a more homogeneous, horizon-free soil that kind of looks similar from top to bottom. Maybe if you give it enough time, a new A horizon will start forming on the top. But again, it can take a long, long time to get new depth of soil, to create new layers. We're talking 50, 100, 150 years in some cases. When you lose that productive topsoil, you also lose a lot of microbes, because the microbes, again, just like the fine plant roots, are attracted to that concentrated source of humus, which is your A horizon. You lose the humus itself, it's spread throughout the entire depth of the soil. And when you lose your humus and your microbes all concentrated in one thin layer of soil at the surface, you lose a lot of the nutrient cycling that would naturally occur in the A horizon, but is not, now that that A horizon is spread out and dispersed to the four corners of the soil. You can find pH changes in urban areas as well too. And a lot of times that can be due to local land use. So wherever you have concrete, there's limestone as a ingredient in concrete. And as that concrete ages and weathers, some of that limestone will dissolve out and flow down into the soil. So sometimes you'll see a little bit of a kind of a boosted pH, a higher, more basic pH in the areas underneath and immediately adjacent to older concrete walkways and roadways. This doesn't sound like a problem, but most of our plants, our native plants around here, actually like soil that's a little bit acidic. So they don't want that basic pH, and it might harm their growth. In addition, there's a lot of fertilizers that can do the opposite. They can lower pH and make things too acidic. And this is especially true of fertilizers that contain either ammonium or sulfur or both. They tend to, over time, cause pH decreases or more acidity to build up in the soil. And why is pH important? Back when I was first learning about soils, I figured, something couldn't grow in acid soil because probably the acid is eating away at its roots. It's not anything like that. It's not extreme like that. Really, what pH does is it affects the availability of nutrients. And generally, our native plants around here like a pH range of about 5.5 to 6.8 because the amount of nutrients that are available within that range are to their liking. It provides the nutrients that these plants need in order to survive. If you start going to a really acid pH below 5 or so, you'll see that some things like phosphorus and potassium and nitrogen start to become unavailable. As these bars get narrower, that means there's less available nitrogen, less available phosphorus, less available potassium. Now, there still might be plenty of NP and K in the soil, but it's not so much the total amount that's there, it's what amount is available to the plants, what amount can be dissolved in that soil water and thus taken up by the plants. Calcium and magnesium tend to become less available at low pH, sulfur as well. Copper and zinc and the other metals like iron and magnesium actually become more available. But as you go to a high pH, those iron metals, iron, magnesium, copper, zinc, they become much less available. So basically, the right pH for the plant, it's the right pH because the levels of nutrients that are available at that pH is to the plant's liking. And again, most of our native plants around here are like a 5.5 to about 6.8 pH, so slightly on the acid range. And then, of course, there's salt. Salt is a big issue for water quality. It's a big issue for utilities because it tends to corrode pipes and such, but it's an issue for soil as well, too, especially soils that are near the roadway. Salt, obviously, if you add too much salt to your soil, it can wilt plants, but it can also destroy the soil structure. And it's kind of an unknown, a lesser known bad aspect of salt. It tends to cause the soil structure, those PEDs, to disperse and break apart. And as a result, the soil just sort of clogs itself up. All the pores become clogged with these broken up heads. So oftentimes it's the soil structure destruction caused by salt that does more damage than the actual drying effect caused by salt. Although certainly more salt can cause more wilting of plants. And the other thing is when we have poor soil in urban areas, it leads directly to poor water quality. Soil quality and water quality are really inextricably intertwined because natural soil acts like a filter and a sponge, sort of like the Brita filter of the world. So both organic matter, especially humus, and clay have these small little electric charges that attract opposite charges, dissolved ions, out of the soil solution, out of the water, and they bind them in soil. And a lot of these dissolved ions, if they were allowed to wash down with the groundwater and down into our groundwater, into our well water, and groundwater is connected to our surface flows as well too, that the groundwater is recharging our streams and rivers in between rainstorms, which is why they can flow throughout the year. If those dissolved ions can get down into the groundwater or the surface water, a lot of times within the water, they become pollutants. In the soil, they're very beneficial generally. In water, they can become pollutants, things like nitrates and stuff like that. If you have bad microbes within your soil, pathogens within your soil, let's say you have some E. coli or something like that, and the goose poop or the dog poop that gets dropped by the sidewalk. We wash that down into our streams and our rivers. Of course, that's a problem as well too. We don't want that bacteria in our streams and rivers. But if you pass those soil microbes down through the soil, if the rainwater washes away some of that waste, washes it down into the soil, percolates it through the soil. Remember, there's billions and billions and billions of bacteria and fungi living in the soil. For the most part, those good bacteria and fungi within the soil will outcompete, destroy, and kill off those pathogen bacteria as that water percolates slowly down through the soil, making its way towards the groundwater. And the water itself is attracted to clay and organic matter. It's not just the ions within the water, but water itself will stick to the surfaces of clay and organic matter like a magnet, which is really important because we want that water to be retained in the soil so that the plant roots can take it up. But we also don't want all that water to flush through the soil immediately, because then it'll get down and potentially cause flooding in our streams and rivers. So soil filters water and it retains a good portion of its volume. And this is very important for the water cycle, not just for soil quality, but for water quality. Because in urban soils, when the soil becomes too dense, that means that there's not the pore spaces to allow as much water to enter into the soil. So we get more stormwater or surface runoff. And as more runoff occurs, we tend to find we get a lot of erosion in the streams themselves. Oops, sorry. So this is my coworker, Willie. He is about 6'7". He's a very tall guy. This is a very typical urban stream right here. As you can see, he's standing a couple feet above the water level, but his head is still a couple feet below the surface or the top of the stream bank. You see the steep stream bank. It's very high, very steep. It's covered with bare soil. It's not covered with plants. And you see these plant roots hanging out into the air, these tree roots hanging out in the air. This is a sure sign of an eroded urban stream. And you'll see this very frequently throughout our urban streams because we have all this compacted soil. We also have these impervious surfaces. So when water falls on the urban landscape, so much of it becomes stormwater runoff. And in addition to that, we've created this drainage system, the gutters on the side of our road, which take that stormwater runoff and channel it quickly and efficiently down into our stream valleys. So basically what happens in urban areas is every time it rains, there's like a little mini flash flood that goes ripping through our stream valleys. This wouldn't happen in a natural area because when rainwater falls on non-compacted soil and non-impervious surfaces, it soaks into the ground and is slowed, and a significant amount of it is retained in the soil itself. But that's not as much the case in urban areas. We get much more of that surface runoff. That surface runoff is channeled directly down into our storm drains and then off into our stream channels. So we get these flash floods, which causes the stream bed and banks to erode out wider and deeper. And this doesn't seem like it's such a huge deal. I mean, obviously this tree is suffering and it'll probably fall into the stream pretty soon. But why is this such a big issue? Well, we've got lots and lots, we've got thousands of miles of these little streams working its way through Arlington, Alexandria, Fairfax, Prince William, Loudoun counties. And if even only a fraction of a millimeter of soil is stripped off their banks and their bed each time it rains, if you add that all up between all the thousands of miles of stream channels we have, we're talking of millions and millions of tons of sediment being washed down into our freshwaters, eventually off into the Potomac, into the Bay. And sediment is actually one of the leading pollutants of the Chesapeake Bay. So to recap, urban development tends to create a dense soil. It reduces the amount of pore space in the soil, which leads to a reduction in oxygen and water available to the roots and microbes because it's not getting into the soil in the first place. In addition, this causes an increase in surface runoff and erosion, especially stream bank erosion. Urban development tends to create a strong soil, which may restrict root growth because the roots just don't have the force or the power to push their way through that dense, strong soil. Development tends to disperse and degrade the topsoil and humus content and kill the fungi. It can change the soil pH, and it can cause the soil to become saltier. So all in all, urbanization typically degrades the fertility and ecological functioning of soil, if we do nothing to correct the damage. And there are things that we can do to correct it, from complicated things to fairly simple things. And what we're seeing in terms of all soil health, but particularly urban health, is that there's this new paradigm of plant health, and that is to focus on the soil. A lot of times we thought of, you go to a nursery and you buy plant food. What is plant food? Fertilizer. What is fertilizer really? Is it plant food? No, it's a plant vitamin. And that's important, but it's not plant food. If you really want to talk about plant, or in this case, we'll talk about soil food, what you have to do is put something in the soil that will feed these guys, the microbes, the bacteria, the fungi, the little insects, the earthworms. If you feed these guys, they will do the work for you, because these guys power the soil food cycle, the food web. And by powering the food web, they're also powering the nutrient recycling that soil can do. As organic matter breaks down as a result of these guys munching away at it, it's releasing nutrients into the soil, which can then be taken up by the plants and allow the plants to be happy and healthy. So what you really want to do is feed the microbes and the other little critters that live in the soil. And in order to do this, you need to give them organic matter, because just like us, they need organic carbon. So again, a soil fertilizer is like a vitamin. Important, but it's not food. You can eat your vitamins in the morning and you're still going to be hungry, and you will be until you have your eggs and bacon and waffles or whatever else you had. Why is that? Because the eggs, the bacon, the waffles, they contain organic matter, specifically organic carbon. And that's what gives us, as well as the soil microbes, their energy. Organic matter, or organic carbon, is the base of the soil food web. It also promotes soil aggregation. As that organic matter breaks down, it becomes humus, and humus is one of those binding agents that causes soil aggregates or soil beds to form. And that leads to good soil structure, which leads again to the good ability of air and water to infiltrate or percolate down into the soil. As you add organic matter, it increases water in the nutrient holding capacity of the soil, because again, as you add organic matter, it breaks down to humus. Humus is very attractive to water. It also bonds nutrients, those dissolved ions, takes them out of solution and bonds them to their surface like a magnet. And humus is also very low density. So you add more organic matter to your soil, you will decrease the density of your soil over time as well too. So here's just an interesting graph that specifically looking at the water content of soil that I think really shows the benefit of adding organic matter. So what you find down here on the x-axis, excuse me, is the soil texture. So imagine we have a really sandy soil over here, and we slowly start adding finer materials like silts and clays until we get up to a loam, which is kind of an equal mix of sand, silt, and clay. And then we move even over to the finer side. So here we have a clay soil, almost like that pottery clay, really, really, really small, tiny particles. So here's a loose, gritty soil, moving our way up to a really sticky, fine soil. As we move from a sandy soil to a loam soil to a clay soil, we find that the field capacity, this is basically the maximum amount of water that the soil can hold, increases. The increase kind of levels off, but it's still increasing. As we get to clay, it's still increasing slightly. But the field capacity is not all that important for us. What's important for us is how much of the water held in soil is available to the plants. And that is the volume of water held between field capacity and the wilting point. The wilting point is, as the name implies, the amount of water in soil below which the plants will start to wilt and droop over. The problem we have with things like clay is that they have a really high field capacity. They can hold a lot of water, but their wilting point is really high. Why is that? Well, they hold water, but they hold it very tightly. They're very greedy with it. So even when there's a lot of water in soil, the wilting point is really high in a clay soil because the water is bound so tightly in films around the surfaces of clays that the plant roots don't have the suction power to extract it off. So what really is important to us is the distance between these two bars. That's the plant available water. The further apart these two bars get, the more water is available to that plant, meaning there's the larger difference between field capacity and the wilting point. We tend to find the most plant available water in the loams. However, the problem with soil texture, again, that's the percentage of sand, silt, and clay, so you can't really do anything to change it. You're pretty much stuck with the texture you have. But if you add organic matter, whether you have a sandy soil, a loamy soil, or a clay soil, you'll see a huge increase in the amount of plant available water. And that's because as you add organic matter and that organic matter decomposes into humus, humus acts a lot like clay in that it can hold a lot of water. So you add organic matter to any of your soil textures and the field capacity is going to bump up significantly. However, unlike clay, organic matter holds water very loosely. Most of the water it holds is available for plant roots to suck up. So it only increases the wilting point by just a little bit. So in all cases, the distance between those two bars has gotten wider, which means the plant available water with those organic matter additions is much greater than when the soil did not have those organic matter additions. So this is just one example amongst many to show you the value of adding organic matter to your soil to help the soil health and help the soil biology and soil food web. So the more available water you have, the happier your microbes are going to be. How do you do it? What ways can you add organic matter? There's many. You can do, I think the best way to do it is to plant, sort of the best, most natural way. Plants exude a lot of organic matter through their roots. They actually find that they benefit by boosting the microbial population in the soil, especially around their roots. So what they do is, as they're creating carbohydrates, as they're photosynthesizing and getting energy from the sun, they're not just putting those new carbohydrates into their own growth. They're actually pumping out a lot of those carbs into the soil, where they are eaten up by the microbes, and the microbes expand in number. They have a big, healthy population, and the more microbes there are, the more efficient that microbial community is at decomposing organic matter and releasing nutrients that can then be dissolved in the soil water and taken up by the plants. So the plants are giving the microbes something that's good for them: carbohydrates, food, organic matter. And as a result, they're getting more nutrients in return from that big, healthy, thriving microbial population. But other than just keeping lots and lots of diverse living plants on the surface, there are other things you can do as well too. One of the easier ones is leaf cycling, and I really push this because it's actually less work for you. So instead of raking up your leaves in the fall, think about just taking out your lawnmower and doing a couple passes over them and chipping those leaves up. And if you can chip them down to about dime size, you'll find that they settle nicely into the cracks between your grass, and it's almost like they disappear. And once they've settled into those cracks, they will, over the next couple months, just slowly break down, decompose, and add organic matter down to your soil. So save yourself some time and do something good for your soil. Leaf cycle. A little more intense, you can even think about something like a compost top dressing. So this is a bunch of piles of compost laid out. This is probably a landscaping company that did this. What they're going to do next is their workers will come out and rake this out into a very thin 1/4 to a 1/2 inch blanket, basically a blanket of compost over the entire lawn that is consistent but not deep enough to bury the grass. So the grass blades will be poking up through it. And over time, your earthworms, your other natural burrowers will naturally mix this compost in with the soil and add all that good composted organic matter down into the A horizon, where again, it's going to really supercharge the microbial soil nutrient cycle. Now, if you do have a really bad soil and a really compacted, having a really hard time growing things on it, there can be a benefit to just throwing up your hands and ripping the whole thing up. Basically laying down some compost, kind of like in the compost top dressing, but rather than just raking it in as a thin blanket and letting the natural burrowers like earthworms work it into the soil on their own time, you can go in with a rototiller and till that material in. I wouldn't necessarily recommend this for your whole lawn. Of course, it's going to tear the whole lawn up. But, let's say if you have an area that's just so compact and nothing's grown, it might work there. Or if you were doing some construction and you know that there was a big construction stockpile in one part of the yard and things are going to be very compacted under there, that could work there. Or if you're taking up an old patio or something and you want to put some new plants down where that patio footprint used to be, the soil underneath the patio is going to be real compacted. So you might want to go in and rototill in some compost to really loosen things up quickly. Now, sort of a big example of this, sort of a large scale example of this, is something called urban soil rebuilding, which is actually a technique that was created by a professor at Virginia Tech called, her name is Susan Day. And it's actually been done in Arlington County. So I'm going to click on this link and hopefully the video of the urban soil rebuilding will pop up. But if you can't see it, please let me know. So I'll go down to the bottom here. Can everybody see the little thumbnail video here? Hopefully you can.
I don't see it, Dan.
Not seeing it? I think I might have to
No.
stop sharing and let me, it's on a different tab. So hopefully this will work.
Of course.
Now are you able to see it?
Now I see it.
So this video was shot by Vincent, the Arlington County forester, who probably many of you do know. I know he gives presentations each year to the to your chapter. All right, let me stop sharing there too. So that was the very technical scoop and dump method of the urban soil rebuilding, where basically you lay out a whole bunch of compost on the surface and you go through with a backhoe and you dip that backhoe bucket down into the soil. You scoop up the soil, you bring it up about 3 or 4 feet above the surface, and then you dump it back down onto the ground. And that's all you really have to do. And Virginia Tech has found that this method, although intense, simple but fairly intense, is really a great way to decompact highly compacted urban soils. Now, a couple of sort of specific things that you see in urban areas. This isn't stuff that people can really do in their own property, but it's stuff that you'll see municipalities do, like Arlington County, Alexandria, Fairfax County, and such. Something called structural soil, which is sort of a compromise between urban needs and plant roots. So urban needs, a lot of cases you do need compacted soil in urban areas. You want the soil under your sidewalk to be compacted. You want the soil under your roadway to be compacted, because if it's not, it's going to start sinking, and then you'll have to repave the road, repave the sidewalk. What structural soil does is try to create a material that has that high strength, which will allow the pavement on top of the soil not to settle or sink, but also has enough pore spaces and loose soil that fine plant roots can work their way through the soil. And structural soil is basically a mix, an aggregation of highly angular particles of stone, basically stone gravel, with soil mixed in. And those highly angled stone particles, they sort of interlock with each other. They mesh together, but because they have such sharp angles, when they pack down together, there are still open, loose pore spaces in between, and those pore spaces are filled with kind of a topsoil-like material. And plant roots can grow through these soil-filled gaps between the stone particles. So the stone holds up the weight of whatever's on top, whether it's a roadway or a sidewalk, while plant roots grow through the loose soil that is found in the pore spaces between the stone particles. So here's an example, so that you can see there's a new seedling planted in that little strip of grass between the roadway and the sidewalk, and what looks like new paving of the sidewalk, sort of an asphalt patch on the sidewalk behind that new seedling. That's actually structural soil. So it's, again, a mix of angular gravel and soil. And what they will do is repave over the top of this, so put another concrete slab on the top. But what the structural soil should do is allow this new sapling to send its roots through the soil-filled pore spaces between the gravel, so it can cross over the sidewalk and then have access to this looser soil in either this yard or this park over here. So this is kind of a way to fix those stunted, spindly curbside trees that I showed on Pennsylvania Avenue, because this is a way to allow the roots to work their way through what normally would be very compacted soil, but instead is working its way through that less compacted structural soil, and then thus having access to this this large patch of decent soil over there. So hopefully that tree will grow nice and tall, because its roots aren't confined into that little strip of grass between the sidewalk and roadway. Then we have something called tree box filters, which you'll see on a lot of newer developments. These are great, but they are pretty expensive. But they're great for street trees. And basically what they are is an underground system of almost milk crate-like boxes. And again, the weight of the paving and roadway on top of it falls on and is supported by the milk crates. And between in the gaps and the spaces in between the solid parts of the milk crate, you can then fill that up with nice loose topsoil, which the tree roots will be able to go through. So it's not compacting the soil. The weight is held by the milk crate itself, which allows for loose soil to be filled in the rest of the filter, the tree box filter. So it's kind of like an underground vault for roots. And here's one being installed. You can see that sort of milk crate structure, the load bearing structure. And once these guys have finished installing that milk crate type structure, then they'll fill this pit in with nice growing soil, nice topsoil growing medium, and then put the plants in. And the plants will be able to send their roots through the soil and snake through that kind of lattice work of, I think it's made out of I don't think it's metal. It's kind of like a really dense plastic. And then there's also flexible paving. You see quite a bit of this in Washington, D.C. So if you happen to be walking down the sidewalk and all of a sudden the sidewalk seems to have gotten a lot softer, you're probably standing on flexible paving. It looks like regular blacktop asphalt, but it's kind of like a rubbery, stretchy material. And what it does is it allows plant roots to grow under it. And it's good for the plant roots because it gives them a little more breathing room for their roots. But it's also good for the sidewalk too, because the sidewalk, unlike hard, inflexible paving, can stretch and move with the plant roots, so it's not always cracking up. And finally, if you're interested in the soil that you have on your property, the best thing you can do is check the soil survey, which is a map of all the soil types in a county. For Alexandria and Arlington, you can go to the U.S. Department of Agriculture's Web Soil Survey, and the URL is right there. It's kind of long, websoilsurvey.nrcs.usda.gov. You don't have to worry about the app part. But really all you have to do is go to Google, go to whatever your search engine is, and type in Web Soil Survey, because there's only one. This is the U.S. Department of Agriculture's electronic digital soil survey. So you can look up soil types basically anywhere in the United States. And for Arlington County, too, they also have a copy of their soil maps up on the county website. So if you go to maps.arlingtonva.us, you can find the digital soil maps there as well, too. Here's a little screenshot of part of the Arlington County soil maps. And that's kind of what they look like. So each of the soils has an alphanumeric code, like 9D4A, and you have to click on it and then look up the legend to see what that alphanumeric code actually means. That's all for me. This is my contact information. So I certainly will take questions now if anybody has some, but if you have a burning question, which you don't think of until tomorrow morning, feel free to send me an email or give me a call in the next week or so, and I will do my best to answer it. But if there are any questions now, of course, I'd be happy to answer those right now too.
Oh, lots of questions.
Okay.
Once you get into plants and stuff, I think some of the early ones you already covered. A lot of questions on how do we make life better for trees that we're planting.
Okay.
And of course, we are going to get into that on the session in 2 weeks on planting, of course, but if you want to just reiterate what an individual can do in their own yard.
Well, the big thing I always say is add organic matter, add organic matter, add organic matter, because organic matter will feed the soil microbes. And I think if you've got a good, healthy soil microbial population, soil health will naturally follow. And a healthy soil will create healthy plants. There's a branch of the Department of Agriculture called the Natural Resources Conservation Service, and they are really promoting 4 soil health principles. It's a little more geared toward agriculture, as you might imagine, but what works for agriculture can work for forestry, for backyards as well too. So they say to maximize the number of continuous living roots. So basically you want to have stuff growing on your soil all the time, as long as you can. Maximize root diversity. So you want to have a lot of different things growing on your soil. Minimize soil disturbance. So for agriculture, that means tilling as little as possible. For us, it means digging as little as possible. I'm not, in a forested land, you probably wouldn't be disturbing it anyway, but basically trying to leave it as is as much as you can without really working your way down into the soil for unnecessary reasons. And maximize coverage, meaning keep something on the soil at all times. You don't want to have bare soil. In forested lands, that's pretty easy. All the leaves falling down create that natural forest duff. That's a great cover. But if you see bare spots in your soil, getting those covered with something, even if it's just a little bit of mulch, is better than leaving it bare. Really, the best coverage is living plants. So in very simple terms, what that means is have things growing on your soil as long as you can throughout the year. Have a lot of diversity growing on your soil. Don't disturb your soil. That's basically it. That's sort of, those are the
Right.
basic keys to soil health.
Okay, someone said that they live in a new community. The builder is planning to cover a hill with Roundup before laying down sod. What should I suggest they do instead? Are there resources for me to better understand their plan? I'm not sure you have control over what's going on, but any
Right.
suggestion?
Well, I mean, talking to the builders is the best thing you can do. I mean, certainly there are options other than sod. You know, maybe you could bargain with them and ask if they could leave certain areas natural and plant them with things that are not going to be grass, maybe with native plants instead, or tree seedlings, things like that. As pesticides go, you know, they all have their issues, but Roundup is about the best one from in terms of its impact on the environment, but obviously it still has its problems. Yeah, I mean, I think it'd be possible to potentially convert some of those areas, take them away from sod and put them into something else. And they might be putting sod on there because they're worried the slope might be so steep that they need to get plant coverage on there real quick. Otherwise it's going to erode and wash away. But perhaps they could think about putting down some natural grass seed mix, some native grass seed mix in certain areas instead of just sod. So at least you'll get native plants. And generally, especially the native grasses, they tend to have a much deeper root system than turf grass. So over time, those deep roots will work their way down into the soil and help decompact it. But yeah, you know, if it's on their approved construction plan that they can do this, there's nothing that can really prevent them from doing it, except for maybe reasoning or bargaining with them and finding some sort of compromise.
Yeah. Someone said we replaced our lawn with garden and winter crops were really helpful to loosen soil and add nutrients.
Great.
Yeah. And then one question, I don't know if you can get into this. It says our street will have a new sidewalk this year. Does Arlington or Alexandria take in account the risk of compaction and use the structural soil? I don't think we do.
Generally, I don't know what the specific laws or regulations are. They would probably only use structural soil around either a newly planted tree or maybe if there's a really high value tree that they were worried about losing. It is a lot more expensive, unfortunately. So it's usually used around some high value species. So if they're putting in a new seedling somewhere, they might put in some structural soil in order to get it to thrive a bit better. So if there are some specific areas, you know, some really nice high canopy trees that you know of, maybe you can make the suggestion that around those areas, they think about one of those alternative paving systems, whether it's structural soil or, in fact, for an existing tree, it might be better to use that flexible paving because with structural soil, you still have to excavate and fill in the
Right.
structural soil. And if you're excavating around living roots, you're basically going to be cutting the roots. So potentially the flex pave on top of those existing tree roots might be the way to go.
Yeah, and that person, I think they should direct message me afterwards and we'll talk, because Arlington County usually does try to avoid trees when they redo the sidewalk. But I can give you some names of directly who you need to contact, because what I've discovered is that the arborist, the urban forester may think one thing's going to happen, but the people out doing the work sometimes pick an easier method to have it work. So. And do you consider lawn with its shallow roots to be an impervious surface, or is that your impervious light?
Yes, it can be. So a lawn, turf grass does have notoriously shallow roots. That doesn't necessarily mean that the soil is compacted underneath, but oftentimes it is. So in many cases, it is compacted impervious light soil. It's never fully impervious. You know, if you've got grass growing on it, it means there's some water and air getting down into the soil, but it just may not be nearly as much as compared to a nice, natural, healthy, low density soil. So yes, impervious light is probably a good characterization of that.
And there was another question on, are there incentives for homeowners to remove blacktop concrete driveways and replace with grass pavers or permeable pavers? And I know there certainly is in new developments in your permitting, but
yes,
what's the answer to that, Dan?
The answer is it depends on where you live. So the last I checked, there was a program in Arlington County called Rainscapes, which would give you cost share reimbursement if you wanted to rip out your paving and install a permeable paving system, or convert some of your lawn into natural landscaping, or put in a rain garden or a dry well or things like that. Unfortunately, I do think that that project has ended. I think the funding ran out. For those of you who live in the city of Alexandria or Fairfax County, there is a program run through my office. It's a state program, but it's run in those two jurisdictions by my office. It's called VCAP, Virginia Conservation Assistance Program. And it's very similar to the Rainscapes program. It offers cost share reimbursement for things like native landscaping, permeable paving, rain gardens, dry wells, infiltration trenches, green roofs, cisterns, things like that. If you're interested in that, send me an email directly and I can tell you how to go about signing up. We take new applications every summer, so then the 2022 application window will open up right around July 1st.
What's your email again, Dan? I'm going to type it into the chat.
It's
What is it?
dan.schwartz@fairfaxcounty.gov.
At Fairfax County, right?
That's right. .gov.
Well, that's the end of the questions. And thank you so much for being with us. And you may get some more questions from people.
I hope so.
Thank you for being with us.
It's always a pleasure to talk to you.
Okay. I'm going to stop recording. Okay. And Dan, you can sit in and listen to us. We were going to have some class time, or, you know, take off and carry on with your life.
I think I'll take off from here, but thank you all for having me.
Okay. Thanks for coming.
Thanks.